There is one element on the periodic table that the entire modern world quietly depends on, and almost nobody can tell you what it is or where it comes from. Right now, as you listen to this, governments are signing classified resource agreements over it. Car manufacturers are in a silent panic about running out of it. And somewhere in the high desert of South America, ancient communities are watching their water disappear because of it. One element, 3 protons, and a story so strange, so full of accidents and wrong turns, that if you tried to write it as fiction, nobody would believe you. Let me tell you something that genuinely stopped me when I first came across it. Almost every metal you interact with today was born inside a star. Iron, copper, zinc, the lead in old pipes, the gold in jewelry. All of it cooked inside stellar cores over billions of years and scattered across the universe when those stars exploded. That is the standard route for the elements that built our world. But the element we are talking about today did not take that route, or at least not mostly. The vast majority of it was produced before a single star had ever switched on. We are talking about the first few minutes of the universe's existence, when space itself was so dense and so hot that nuclear reactions were happening in open space, without any star needed to drive them. Physicists call this primordial nucleosynthesis. It is the period when hydrogen formed, when helium formed, and when tiny traces of this element were cooked into reality almost as an afterthought. Roughly 1 atom of it for every 10 billion hydrogen atoms. A whisper of a presence at the very beginning of everything. And here is where it gets uncomfortable in the best possible scientific way. Our best models of that early universe, the equations that describe what happened in those first minutes, make a very specific prediction about how much of this element should exist out there in the oldest stars. The ones that formed directly from primordial matter before anything else had a chance to contaminate the mix. The prediction is precise, the observation is consistent, and the 2 numbers do not match. The oldest stars contain roughly 3 times less of this element than the physics says they should. 3 times less. This is not a rounding error. This is not an instrument calibration issue. This is a real, documented, unresolved discrepancy that astrophysicists have been sitting with for decades. And nobody has a confirmed answer yet. Several hypotheses exist. None have been definitively proven. The gap is still open. I want to sit with that for a moment because I think it matters more than it might seem. We are talking about an element that is absolutely central to modern technology, to medicine, to weapons, to the future of energy, and its very origin in the universe contains a mystery that our best science cannot yet close. That is not a weakness of the science. That is actually what good science looks like. It is precise enough to find its own gaps, honest enough to leave them open, and stubborn enough to keep working on them. Most things we call knowledge are actually just the best available answer right now. This element, from its very first moments of existence, refuses to be fully explained. And it has been refusing ever since. Because the story of how it was actually found on Earth, and what people did with it once they found it, is somehow even stranger than its cosmic origin. Friends, if this kind of deep dive into the hidden science behind the things that shape our world is something you enjoy, subscribing and leaving a like genuinely helps this channel keep going. It takes real time to dig into stories like this one. And every bit of support makes the next one possible. Now, a cold morning in a northern European laboratory, a routine mineral sample sitting on a workbench, and a young researcher who was absolutely not looking for what he was about to find. The sample came from a volcanic island in the Baltic Sea, collected as part of a survey project that was, by all accounts, deeply unglamorous work. Cataloging rocks, measuring compositions, filling in tables. The kind of science that does not make anyone famous. But something in this particular sample was behaving wrong. When the researcher ran it through the standard procedures used to identify alkali metals, the numbers came back off. The substance dissolved differently than expected. It reacted at the wrong rate. And when a small amount of it was introduced to a flame, the color it produced was not what any known compound should have made. The researcher brought his findings to his senior colleague, one of the most respected chemists of the era, the man who had personally introduced the system of letter symbols for elements that every chemistry student still uses today. The senior colleague examined the data, agreed that this was something genuinely new, and suggested a name drawn from the Greek word for stone. The reasoning was simple and slightly poetic. Every other alkali metal known at the time came from organic sources, from plant ash, from biological material. This one came from rock. It was the exception. It lived in stone when everything like it lived in living things. The name stuck. The substance, however, remained stubbornly difficult to isolate in its pure form. Several researchers across different countries attempted it over the following years, using electrolysis of molten compounds, coaxing tiny silvery beads out of heated salts. When they finally held pure samples of it, those samples immediately began reacting with the air in the room. A film of gray oxide and nitride formed on the surface within seconds. The metal was announcing from its very first moments of exposure that it did not intend to sit quietly and be studied. It would need to be stored in oil to survive. It would float on water and react with it, fizzing and heating and releasing hydrogen gas, not violently like some of its neighbors on the periodic table, but insistently, restlessly, like something that cannot stop moving even when you want it to hold still. At this point, the scientific community had a name for it, a rough sense of its behavior, and almost no idea what it was actually good for. That question, what is this thing actually for, would be answered many times over the next 2 centuries, in ways nobody in that Northern European laboratory could have imagined. Some of those answers would save lives, some would end them, and at least one of them would end up in a drink that billions of people have consumed without ever knowing what was once inside it. The drink that contains this metal has been sitting in refrigerators around the world for nearly 100 years, and the people drinking it have never been told the full story of what used to be inside it. That is not a conspiracy. That is just how quietly this element moved through the world before anyone understood what it actually was. So let me take you back to a period when the science around this metal was thin, the marketing was thick, and the line between medicine and commerce was essentially invisible. Wealthy families in Europe and North America were visiting highland spa resorts where the water was described as naturally invigorating. Some of these springs genuinely contained trace amounts of this element dissolved in the groundwater. People drank the water and reported feeling lighter, calmer, more themselves. Doctors at the time were not fabricating these reports. Something was happening, even if nobody could explain the mechanism with any precision. The problem was that the observed effect, whatever its true source, became a commercial opportunity long before it became a scientific question. Tonic drink manufacturers began adding small measured amounts of a compound containing this element to their products. The bottles carried labels with language that today would be illegal in most countries. Words like restorative, mood balancing, and nerve tonic appeared in large letters above lists of ingredients that most consumers could not have identified. The drinks were not sold in pharmacies. They were sold in general stores, advertised in newspapers alongside furniture polish and garden seed, positioned as something a responsible household simply kept on hand. One particular lemon and citrus-flavored drink became especially popular across the eastern seaboard of North America, marketed specifically at working families as a way to recover from a long week, sharpen the mind, and lift the spirits of the whole household. The amount of the active compound in each serving was not huge, but nobody had defined what a safe daily amount looked like, because nobody had run the kind of careful, controlled study that would answer that question. People bought the drink, felt something they described as better, told their neighbors, and the product spread. Over time, the manufacturer reformulated the recipe, quietly dropped the element from the ingredients, and changed the name to something shorter and simpler. That name is still on shelves right now. You have almost certainly bought it. And the element that gave the original version its selling point has been gone from the formula for decades, with almost no public record of it ever being there at all. Now here is where the story turns from darkly amusing to genuinely troubling. Because while this drink was being sold to families as a pleasant wellness product, the same element was simultaneously moving through the medical system in a very different way. And the consequences of that parallel journey were far more serious than any bottle of flavored water. Physicians working with patients who had severe heart conditions were under pressure to reduce sodium in their diets. Salt was the problem. The body needed something that behaved chemically like salt, but without the same cardiovascular consequences. Someone decided that a compound containing this element fit the description. It dissolved similarly. It tasted roughly similar. And so it began appearing in hospitals and clinics as a sodium substitute, handed to patients who were already unwell, given without precise dosage instructions, and in some cases, taken home to be used freely at mealtimes like ordinary table salt. The element has what chemists call a narrow therapeutic window. That phrase sounds technical, but the meaning is simple and frightening. The gap between the amount that does something useful and the amount that causes serious harm is small. Dangerously small. When patients who were already physically compromised began consuming this compound in uncontrolled quantities, their bodies could not handle it. Some developed tremors. Some became confused. Some did not recover. The cases were documented. The reports reached regulators. And the regulatory response, when it came, was fast and sweeping and almost completely undiscriminating. Everything involving this element in a medical context was effectively shut down. The ban landed on the dangerous misuse and on every legitimate avenue of research at the same time, because in a moment of public alarm, nuance is the first casualty. A prominent figure in the psychiatric establishment, whose word carried enormous institutional weight, had already declared years earlier that this element was simply too dangerous for clinical medicine. The poisoning cases seemed to confirm exactly what he had said. His verdict, already treated as settled fact, now had tragedy behind it to make it feel permanent. What nobody paused to examine in that moment was the actual source of the harm. The patients who had suffered were not receiving carefully calculated doses under medical supervision. They were seasoning their food with an unregulated compound in quantities nobody had measured or monitored. The element had not failed as a medicine. It had never been properly tested as one. The ban arrived before the test could happen, and it would hold for long enough to delay one of the most significant discoveries in the history of psychiatry by more than a decade. Somewhere on the other side of the world, completely unaware that any of this was happening, a hospital physician was about to stumble onto something that would eventually overturn the entire consensus, and he was going to do it in a room that most research institutions would not have dignified with the word laboratory. A doctor with no research budget, no dedicated laboratory, and no institutional support just overturned half a century of medical consensus using a spare room, a colony of small animals, and a compound that the rest of the world had just declared too dangerous to use. And the most extraordinary part is that he was not even looking for what he found. The facility where he worked sat on the outskirts of a mid-sized city in the southern hemisphere, far from the academic centers where reputations were made and journals were edited. The building smelled of floor disinfectant and old wood. The wards were full and the resources were thin. This physician, a quiet and methodical man who had spent years watching his most severely ill patients cycle through states of agitation with no effective intervention available, had developed a private theory. He believed that the urine of patients in acute manic states contained some kind of biological substance that was driving their symptoms. His plan was to isolate it, identify it, and find a way to neutralize it. The tools he had available were basic: a centrifuge, some standard reagents, a collection of guinea pigs housed in a room that also stored cleaning supplies and spare linens. He began separating patient samples into fractions and testing each fraction by injecting it into the animals. The work was slow and largely unremarkable for weeks. Then one afternoon, he needed to improve the solubility of a particular fraction before testing it. And he reached for a compound containing the element we have been talking about throughout this entire story. The same element that had been sold in tonic drinks. The same one that had just been banned following the poisoning cases on the other side of the world. He added it to the mixture simply because it dissolved uric acid compounds effectively, and he needed the solution to move through the syringe cleanly. The animal did not convulse. It did not react with distress. It settled. It moved to the center of its enclosure, lay down on its side, and went still in a way that looked less like sedation and more like genuine calm. He watched it for a long time. Then he repeated the experiment. Same result. He increased the dose carefully over several trials, watching for toxicity, watching for the point where calm became something worse. The window was narrow, as it always is with this element. But it existed. The animals became quieter at therapeutic levels without losing function. He was not imagining it. The decision to move to human trials came from a place of genuine desperation, and it is important to understand the context. There were no effective treatments for acute mania at that time. The options available were restraint, sedation with substances that left patients barely conscious, and a surgical procedure being introduced in those years that modified brain tissue permanently. Against that backdrop, a physician who had observed a consistent calming effect in animals and had carefully mapped a safe dosage range made the decision to try. His most severe patient was a man who had been in a state of continuous agitation for several years. The staff had essentially stopped expecting him to improve. He could not hold a conversation. He could not sleep through a night. He had lost so much weight that the bones of his face were visible. Within days of beginning the compound, the man slept. Not a drugged unconsciousness, but actual sleep, the kind that ends with waking. Within a few weeks, he was eating at a table with other patients. Within 2 months, he was well enough to be discharged. He went home. He worked. He lived for years afterward, maintaining his recovery as long as he continued the treatment. The physician documented everything and submitted his findings to a medical journal. The paper was published. And then, from the international psychiatric community, came almost complete silence. The ban that had swept through the regulatory landscape was sitting over everything like a ceiling, and the most influential voice in the field had already ruled on this element years before the physician's paper ever appeared. His findings were not refuted, they were simply not engaged with. No major journal reprinted the work. No large research institution followed up. The discovery sat in the published record like a message written in a language nobody at the top of the profession was willing to read. It would take another decade and the work of researchers in Scandinavia and North America running their own systematic trials before the evidence became impossible to dismiss. And by the time it was finally accepted, the question hanging in the air was an uncomfortable one. How many people could have been helped during those lost years if the field had looked at the data instead of the ban? But while psychiatry was busy not paying attention, another set of institutions had found this element and had very different plans for it. Plans that had nothing to do with calming anyone down. The first sign that something significant was happening came not from a scientific publication, but from a classified procurement order filed through a government supply chain that did not officially exist. A facility in a remote region, built rapidly and largely underground, had placed a request for quantities of a lithium compound that made no sense in any civilian context. The numbers were industrial. The security classification attached to the order was the highest available, and the stated purpose was listed under a project code that meant nothing to anyone outside a very small circle of physicists and military planners. What those planners had realized was this: the element that a physician in the southern hemisphere was quietly using to calm a single patient in a sparse hospital ward was simultaneously the key to producing the fuel for the most powerful weapon ever conceived. Not the whole element, one specific version of it. Natural deposits of this metal contain two distinct forms, two isotopes, present in very different proportions. The lighter of the two, making up less than 8% of any natural sample, turned out to be uniquely reactive in a way that weapons designers needed urgently. When struck by a neutron under the right conditions, it splits and releases a specific form of hydrogen that burns at temperatures matching those inside stars. That hydrogen is what makes a thermonuclear weapon function. Without a reliable supply of this isotope, the weapon cannot be built. So the race to separate it began. In facilities on two separate continents, running in parallel and in complete secrecy from each other, industrial programs were launched to take natural deposits of this element and pull the two isotopes apart. The process required enormous infrastructure. It also required mercury, enormous quantities of it, used in a chemical exchange process that allowed the lighter isotope to be concentrated gradually over many cycles. The mercury moved through the system continuously, and some of it did not stay in the system. It seeped into soil. It entered waterways. It accumulated in the surrounding environment in concentrations that would take generations to fully measure and longer than that to address. The heavier isotope, the one making up more than 90% of natural deposits, was considered worthless. It came out the other end of the separation process in bulk and was stored in containers in warehouse facilities, accumulating year after year as the weapons program consumed the lighter fraction and discarded the rest. Thousands of tons of a material that nobody had a use for, piling up in the shadow of a program designed to build weapons capable of leveling entire cities. The element that had floated on water in a northern European lab, been sold in a citrus drink, calmed a desperate patient in a sparse hospital room, was now at the center of the most consequential arms development program in human history. And the part of it that was being thrown away was about to become something nobody expected. The material that weapons engineers had been throwing away for decades turned out to be exactly what the future of clean energy needed, and the people who realized this first were sitting inside the same classified programs that had been generating the waste in the first place. That is not a comfortable irony. It is just the truth of how this element moves through history, always ending up somewhere nobody originally planned to put it. So let me explain what happened to all that discarded heavier isotope, because the story takes a turn here that I find genuinely difficult to wrap my mind around even now. The separation facilities had been running for years, pulling the lighter isotope out of natural deposits and stockpiling the heavier remainder in sealed containers. The heavier isotope was considered a processing byproduct. It had no weapons application. It was chemically stable, relatively inert under most conditions, and accumulated in quantities that eventually became logistically inconvenient. Someone had to decide what to do with it. Nuclear engineers working on reactor design problems noticed something specific about its behavior under high-temperature conditions. It conducts heat exceptionally well. It flows easily when melted. It does not become dangerously radioactive when exposed to neutron bombardment inside a reactor core, which is a property so rare and so valuable in that environment that it is almost hard to believe it comes naturally. A liquid metal coolant that carries heat efficiently without itself becoming a long-term radiation hazard is exactly what certain reactor designs require and almost never find. The heavier isotope that weapons production had been discarding fit that description almost perfectly. Research programs began testing it in experimental reactor configurations. The results were consistent enough to attract serious attention. Then came the larger realization, the one that reframed the entire picture. Fusion energy, the process of generating power by fusing light atomic nuclei together the way the sun does, requires a specific fuel that does not exist in nature in usable quantities. That fuel has to be produced inside the reactor itself, generated continuously from a surrounding layer of material that absorbs the high-energy particles released by the fusion reaction and converts them into fresh fuel as it does so. The material best suited for that surrounding layer, that regenerating blanket, is the heavier isotope of this element. The waste product. The thing being stored in containers because nobody knew what else to do with it. The largest international fusion research project currently under construction, a facility being built through a collaboration involving dozens of countries, is designed around exactly this principle. The heavier isotope sits in a layer around the fusion plasma. Particles pass through it. Fuel is generated. The reaction sustains itself. And the material that makes this possible was produced as a byproduct of a weapons program that considered it worthless. Something built to destroy is quietly becoming the foundation of the most promising clean energy technology humanity has ever attempted. The element did not change, only what we decided to do with it did. I keep coming back to that thought as the story moves forward, because what comes next follows the same pattern in a different industry, and the similarities are striking once you see them. The rechargeable battery that now powers hundreds of millions of vehicles and devices around the world did not arrive through a clean, well-funded, logically sequenced development process. It arrived the same way almost everything in this element's history arrived, through accidents, rejections, institutional indifference, and one or two people who refused to stop working on something that everyone around them had decided was not worth pursuing. The foundational chemistry was worked out by a researcher employed by a petroleum company, which is almost too ironic to say out loud. A scientist working for an organization whose entire business model depended on the continued dominance of combustible fuel developed the basic electrochemical architecture that would eventually make that fuel less necessary. The company held the relevant intellectual property and did very little with it. The commercial opportunity was not something they were motivated to develop. The research sat. The next critical advance came from a materials scientist who was, by any conventional measure, past the point in his career where major breakthroughs were expected. He was in his late 50s, working in a university laboratory with a modest budget and a small team. And he identified a cathode material that solved a fundamental problem the earlier work had left open. His solution made the battery stable enough and energy-dense enough to be genuinely practical. He published. He filed patents. He waited for someone in his home country to see the commercial potential and move on it. Nobody did. The rights traveled across the Pacific Ocean to a team of engineers at a consumer electronics company who were trying to solve a very specific and unglamorous problem. They needed a smaller, lighter power source for a portable video recording device. They built a production version of the battery, put it into their product, and released it to the market. The device sold. The battery inside it quietly changed everything. Within a few years, the same battery architecture was in laptop computers, then in mobile phones, then in medical devices, then in vehicles. The demand for the raw material grew at a rate that nobody had modeled for, because nobody building the original consumer electronics product had been thinking about electric cars. The element that had floated in mineral oil in a northern European lab, been dissolved into a citrus drink, calmed a patient in a sparse hospital ward, fueled weapons programs on 2 continents, and been discarded as industrial waste, was now being extracted from the ground at industrial scale to power a global energy transition. And the places where it existed in the largest quantities were places where the people living above the deposits had not been part of any conversation about what was about to happen to the land beneath their feet. This element is inside you right now, and you almost certainly have no idea. Not as a medicine, not as a supplement, just as a trace presence in the water you drink, the food you eat, the air that moves through certain buildings you walk into without a second thought. It is so embedded in the structure of modern life that removing it would not feel like losing one thing. It would feel like the world quietly coming apart at several seams simultaneously. Let me show you what I mean, because most people think of this element in two contexts only: batteries and psychiatric medication. That is like describing the ocean as something you occasionally swim in. The actual picture is so much wider that it genuinely changes how you see the world around you once you understand it. Start with aircraft. The alloys used in the structural components of modern passenger jets contain small percentages of this element mixed into aluminum. The result is a material that is simultaneously lighter and stiffer than standard aluminum alone. Every kilogram removed from an aircraft structure is fuel saved across thousands of flights over the lifetime of that aircraft. The savings accumulate into figures that are difficult to visualize. Hundreds of tons of fuel per plane across a global fleet across decades. The element that floats on water is holding you in the air when you fly. Now think about the machine that packed the boxes in the warehouse that shipped you whatever you last ordered online. The joints, hinges, and bearings inside that machine are almost certainly coated in a grease formulated with this element as its base. Roughly 7 out of every 10 industrial lubricants in the world use it. It works across temperature ranges, from deep winter cold to the heat of active machinery, without breaking down, without leaking, without hardening. The global manufacturing infrastructure runs on it in a way that is almost never discussed because it is so ordinary and so invisible. The screen you are most likely using to watch this video right now is harder and more resistant to impact because of this element. It is added during the glass production process, reducing the temperature required to melt the raw material and improving the structural properties of the finished product. The coffee cup on your desk may contain it in the ceramic. The windows in your car almost certainly do. It is in the glass of the buildings you pass every day, and nobody has put a label on any of it telling you so. Now here is the one that genuinely stopped me when I first read about it. People with certain heart conditions are alive right now because a small device implanted inside their chest has been running without interruption for a decade or more. The battery powering that device uses this element. It has to be reliable over a time frame that almost no other battery technology can match, inside a human body, with no possibility of recharging or replacement without surgery. The primary non-rechargeable version of this element's battery is its own enormous industry, entirely separate from the rechargeable batteries in vehicles and phones, and it keeps people alive in a way that has become so routine that the technology behind it is rarely mentioned. Submarine crews breathe recycled air because of a chemical reaction involving a compound of this element that absorbs carbon dioxide and releases oxygen. Research accelerators and electron microscopes maintain their internal vacuums because of getter materials containing it. Solar power plants in Spain and the American Southwest store heat from afternoon sunlight in molten salt mixtures that include it, and use that stored heat to generate electricity through the night. Early clinical studies suggest it may slow the progression of certain neurodegenerative diseases. Agricultural researchers are investigating whether trace amounts of it in soil help crops survive drought conditions. The molecular mechanism appears to be the same one that makes it effective in treating certain psychiatric conditions, operating in plant cells as it does in human neurons, suggesting this element is involved in biological processes that existed before animals and plants were separate things at all. 3 protons, 1 valence electron, present in the first minutes of the universe, sitting in mineral rock for billions of years, dissolved into the groundwater of ancient highland basins, and now threaded through virtually every system that modern civilization depends on. That is the invisible part of this story, and it makes what comes next feel even more significant. Because the element itself has never once changed. Not a single proton added, not one removed. It is identical today to what it was in the first moments of existence. Every single development in this entire story, every accident and breakthrough and disaster and revolution, belongs entirely to the choices made by the people who found it, used it, misused it, banned it, weaponized it, discarded it, and eventually built the modern world around it without most of those people ever realizing that is what they were doing. The physician working in a sparse hospital room with no funding and no recognition was doing the same thing as the material scientist whose breakthrough traveled across an ocean before anyone in his own country paid attention. Neither of them was trying to change history. Both of them were just doing their specific work honestly, in difficult circumstances, with the tools they actually had, rather than the tools they wished they had. That is not an inspiring speech. That is just what the record shows. But here's the part of the record that does not resolve neatly. The communities living above the largest deposits of this element in the high desert regions of South America were not consulted when the decision was made to extract it at industrial scale. The water tables in those regions have dropped measurably. Rivers that fed ecosystems and sustained ways of life stretching back centuries have become shallower. The people most directly affected by the physical extraction of the material powering the global clean energy transition are among those with the least ability to influence how that transition happens or who bears its cost. The environmental ledger from the weapons programs that first separated its isotopes industrially is still being settled in contaminated soil and waterways by communities that had no connection to the decisions that created the problem. Progress in this story has never been free. It has always been paid for by someone. And the consistent pattern across every chapter of this element's history is that the people paying the cost and the people making the decision have almost never been the same group. That is not an argument against progress. It is an argument for honesty about what progress actually looks like when you follow it all the way down to where it lands. On specific land, in specific water, in specific lungs, in specific communities that rarely appear in the press releases announcing the next great technological leap forward. This element is 3 protons old. It has been here since before stars existed. It will be here long after every decision we are currently making about it has played out. The only question it cannot answer for itself is the one that has always belonged to us. Who decides who pays? Now, I want to ask you something directly, and I genuinely want to know what you think. If the clean energy future that everyone agrees we need is being built on a foundation that is visibly damaging the land and water of communities that had no vote in the matter, does that future still deserve to be called clean? Write your answer in the comments. I am not asking for agreement. I am asking for your honest thought. If this kind of story is what you come here for, a like and a subscription tells the channel to keep making them. It takes real work to dig this deep into a single element, and every bit of support makes the next one possible.